Okay. Hi, welcome to this class on Intro to Mixture Designs. I'm Dana Kruger, and I'm hopefully going to introduce you a little bit today to the power of mixture designs so that you'll know when to use them, which one to use, and how to interpret the results. And we'll walk you through several things. But first, I wanted to tell you why it's so important to me that we not skip over this. So we're at the towards the end of our semester in learning about experimental design, fractional factorials, response surface methodology. And I want to tell you my story that I graduated with a bachelor's degree in chemical engineering and began work as a compounder for synthetic rubber products right after graduation, working in research and development, and never had even a statistics class. Wasn't required. I wanted to avoid any additional Greek letters. So I avoided a stats class, didn't even think about it. I had never heard of designed experiments until I started working, and there was a class that we were kind of required to go through on Taguchi designs. And so we've talked about those earlier in the semester and kind of the differences and trade-offs between that approach and other experimental um, designs. And um, never heard about mixture experiments. Well, I get a master's degree, take a course in designed experiments, learn more about that. And I'm amazed that that wasn't taught in my workplace, and went on to PhD study. But before I go on to that, which is where I heard about mixture designs a couple years in, but I have with me two black rubber balls, which may not be very clear on the video. They are exactly the same size. They are You can tell a slight visual difference. One is a little bit grayer than the other. But my job right out of college was to help determine which ingredients and which amounts of which ingredients would go into synthetic rubber products so that they could do what they needed to do in the field for different applications. And you can think for synthetic rubber, there's lots of different applications. There's tires, there's golf balls, there's belts, there's hoses, lots of different things. So these balls look the same, but it's what's inside that matters, right? I don't know if this will work very well. I'm going to try to bounce this ball and show you. This is the kind of slightly grayer one. And so it bounced pretty well. It bounced off the screen. Here's the other one, and it just falls and stays there. And so creating the right mixture with the right ingredients and the right amounts really has a huge impact on the properties of this product, of what rubber can do. And we're going to talk about other kinds of mixtures that we might see in life as well. So I'm going to move on. In this brief time, I want you to walk away with understanding when you need to use a mixture design. There's several different types, so I want you to be able to kind of have an idea about which type is going to fit your needs. I want you to understand kind of some of the steps to take through and some of the software that might be available. And also, then what do you do with the results? How do you make a recommendation? How do you use that information to make a decision, take that next step forward? So we'll talk a little bit about that, just kind of as an introduction. We're not going to be heavy on the math today, more practical discussion. But I wanted to introduce this by kind of telling you how I've been thinking about mixture experiments more recently in my life. Does anybody know who this is? Well, maybe you recognize him as Mark Rober. And my family, my kids and I know him from YouTube. From at the time, a friend of mine told me, hey, there's this really fun squirrel obstacle course video. You've got to see it. And so we've been watching his videos. And in 2019, he set out to set the world record for the world's largest elephant toothpaste. And you can see here in the picture that this was on a large scale, filling a swimming pool. And if you watch this video, it oozes over the side. He uses a mixture here. I have the recipe. They wanted to make it safe so they could play in the bubbles afterwards. So they used a concoction with yeast. And I've done this experiment for chemistry classes for kids, and it's fun. So you can see that we've got yeast, hydrogen peroxide, dishwashing soap, and warm water and food coloring are the main ingredients that go together in this mixture. And the result is this kind of oozing out of the bottle, and it keeps going and going for some time. Well, this record was superseded not long after that. And so in 2020, Mark Rober went back to the drawing board, says, elephant toothpaste was fun, but let's see if we could do something a little bit more explosive. So this is when he changed to devil's toothpaste. And if you've seen this video, you can see it's a lot more kind of spectacular kind of reaction. But as he's talking through this 20 or so minute video, he mentions doing over 150 tests. And as I'm watching this for probably not the first time, probably the second or third time with my kids, this just really stood out to me. And so he mentions with this testing, looking at the right scaled up neck dimensions. Does the neck length matter? So he tests a control 22 inches, 33 inches, 55 inches, different settings. And we've talked about in factorial design, this is what we're kind of used to. But then he also talks about varying the amount of dish soap with these different volumes. And you can see here are the different settings for this screenshot of soaps here. And they're measuring it by the height of the kind of eruption by these lines on the wall with photography to compare how much it's going to shoot up and how the soap impacts it. And then we've got different brands of food coloring that they were testing as well. Something you can see in this screenshot is that here he's got different tests and he's got milliliters. So I think this has to do, I don't know exactly what he's measuring here, but different milliliters. So I feel like this is something he's changing. And then here it looks like the response variable height, and he's got those responses there and some kind of ratio. And as I'm seeing this and hearing him talk through this, I think it really sounds like he's doing all this experimentation one factor at a time, which in all honesty is what we're taught from like elementary school all the way through, unless you've had a design of experiments class or in industry or in school. Not everybody has that. There's lots of people working in science and engineering that have never heard about fractional factorial design or just more efficient designs that can give us more information about the interaction terms. And so this just really bothered me. I thought, I just don't know if he knows about designed experiments. So maybe I should really write to him in a very respectful way and just ask, and because I don't want him to miss out. And what a great platform if Mark Rober could be teaching kids early on about the power of designed experiments, and how much time and money would he save if he could experiment more efficiently with these methods. So told my kids I was going to write it, and they were all excited. I didn't write it, and I didn't write it. I finally did this semester, and I copied myself, and I went straight to my spam folder. So I don't think he even saw it. I expect that he went to his spam folder as well. And I got to thinking, maybe that's how it's just supposed to be. He was a NASA engineer, right? And the friend that I have that worked for NASA, she's brilliant. Everyone at NASA must be brilliant, I think. She has her black belt in Lean Six Sigma, and design experiments is a big part of Six Sigma, right? So I think everyone must be trained on design experiments in NASA, just like they were at Intel when I had to take a short course on design experiments there for a 10-week internship. So I think, okay, maybe I'll just let it be. I was just kind of ridiculous there. But then I went to a conference this fall, spoke to another brilliant NASA engineer who addressed the entire conference, gave a great talk, but he let us know that NASA projects are not required to reach out to the statistics department. And it's available, but they're not required to. And so I think it is completely possible that you could have graduate degrees in engineering, have a team of people together that just aren't familiar with these tools, that don't know to reach out and ask some questions. Um, and so maybe he could still benefit from learning more about experimental design. And for this one, mixture experiments. Well, if you've watched the video, you know how this turned out. And he was able to set the new world record using this devil's toothpaste with this incredible eruption off the top. But he wasn't satisfied because his Erlenmeyer flask that he had created here didn't hold together at the bottom. There was just so much force pushing as that catalyst made that reaction happen. So he tried again and the next year, and you can see how huge and how high this devil's toothpaste experiment went. It is just incredible. But let's get on and talk about mixture experiments. Now, the part I didn't emphasize with this, if we go back to our factors, lots of these are typical factors that are independent of everything else. Neck length, you can vary that. It's not going to impact anything else. But what happens when you vary the soap? When you're varying the soap, these amounts, that impacts the rest of the mixture. So as you increase the proportion of soap, proportions of other ingredients in the mixture are going to be decreased because they all have to add up to 100%. So we're going to be talking about these cases. Mixture experiments are response surface experiments that have this special constraint that they're all going to add up to 100%. And we want to figure out what blend is optimal to give us the result that we're hoping for, to maximize or minimize some property. If we look at a cake baking example, we've got settings that could be used with factorial or response surface if we vary time and temperature. Let's say we're looking at the moisture in a cake. We can have the baking time set at 20 minutes and vary the temperature. We can have the temperature set at a particular, at 350, let's say, and we vary the time. How moist is it from at 20, 22, 24, 26, 28, 30 minutes? We can do that. They're independent of each other. That's pretty typical. But as I said, with mixtures, we've got these ingredients that have to go together to add up to 100%. And that's a constraint that we have. The amount of each ingredient depends on the others. So we want to remember, friends don't let friends use factorial designs if they're mixtures. There are several different types of mixture designs, and I want to give you a little bit of introduction to each of them because you might see these options in the software. And I'll show you in JMP kind of where these are displayed as options, and but we'll talk about what they mean first, several of them. We'll start with simplex designs. We'll look at simplex lattice and simplex centroid. There's also extreme vertices, there's optimal designs and space filling designs. So those are the ones that we're going to talk about a little bit today. The simple lattice design is just looking at, sometimes is, let's just see if we can draw it. I can get, okay. All right. let's say we have three different factors we're looking at. And so I'm going to draw the design space as a triangle with x1, say x2, and x3. So we've got, three components. So the P is going to be our 3. And we've got M is going to be how many points we want to look at. So if we want to look at 0 and 1/2 and 1 for each of these, then M is going to equal 2. And we would have these 6 design points. And if we look at what they are, we'll have 1, 0, 0, 0, 1, 0, 0, 0, 1, 1/2, 1/2. I'm going to run out of room, aren't I? And 0, 0. I'm going to switch to 0.5 so that I can maybe fit this in here. 0.5 and 0.5. And 0.5, 0, 0.5. Okay, and that's what we would be running. And then we would look for our responses. We would have our Y here. And we would randomize these as we've learned about. We would want to have replicates. We'll reiterate that later as well. But this is one example. If we have more components, I'm not so good at drawing this, and I've got this on a slide later, but we would have another dimension. So I don't know, something like this, and then the same kind of thing. We'll just highlight it on the next slide. So that's a simple simplex lattice. There's also the simplex centroid, because you can see that a problem with this triangle here is that we don't have any center points. There's nothing in the middle. So if we're needing to know what happens in this middle space where we have more combinations, there's only 2 ingredients being tested together at any one time with the simplex lattice design. So we can use the simplex centroid to simply add a center point. And so we'll have this as a number of runs for that situation. Here are some more professionally drawn figures of the design space. So if we add another M in that equation and say, hey, we want to test at 3 different levels, a 0, 1/3, 2/3, and 3 for each of my 3 components, then that's what this lattice is going to look like. If we have 4 components, we have 4 corners. I drew it wrong. We can see if we have just 2 levels that we want to check, and then if we have 3, what that looks like in these pyramids. Where for the simplex centroid, here's that center point, and that's going to make these center points along each face of the pyramid. We can also augment these simplex designs. We can add design points kind of wherever we want, but you can see here from that simplex centroid, we've added this, this point and this point and this point are new. We had this in the simplex centroid, but not the simplex lattice. So that gives us more information about what's happening in the center of the triangle of the design space to help us kind of better understand, get more information. So we can augment those. Optimal designs, as I was listening to a talk by someone who, from Design Expert, he said that this is really all that he sees in real life, for the most part, is the need to use optimal designs. Well, why? If you remember the triangle, well, let's start with this. We've got different constraints. Let's say for one reason or another, one of our ingredients, we can only use these amounts. It can only be between 0.2 and 0.8. Same thing for this second one. And this one can be between 0 and 0.6. So for this example, we are not going to be interested in anything outside of this smaller circle here. And if we use that simplex method, either way, we're going to have these perimeter points that aren't going to be meaningful at all. That's just kind of a big waste because those aren't even possible with the constraints that we have. We would have one, like this one, would be the only one. So it wouldn't be efficient for us at all. We need to look at the design space that's real for our situation. So optimal designs will better account for those linear constraints we might have in the mixture and be able to look at the design space, maybe shrink it into a triangle that fits. Maybe it's not even a triangle shape. Maybe there are parts cut off where like, oh, it's not even this part. And just being able to work around that and to create a design using D-optimality or I-optimality, and different software will use different kinds of methods. Another option is space filling designs. And I'll show you where this option is in JMP. You can see the default was to have 30 runs. And here it'll just tell us for our 3 different components what the settings need to be. And so again, if we have constraints, we can set that up. And then wherever those constraints are, I don't know, maybe it's even something like this upside down triangle, just to kind of evenly space throughout the design space of interest, where we can get some more information. So let's look at an example. This example, I was surprised. I looked in one textbook and it had this example reference from a book. I looked at another source online from Air Force Institute of Technology. They used the same example. Looked at another source. I found this example. So I don't have my book handy, but Cornell's book on mixture experiments is where this example originated. And it uses 3 components to make a yarn. It's going to look at a blend of polyethylene, polystyrene, and polypropylene to blend those together to make a fabric for draperies. And the way it's going to look at the response is going to look at the thread elongation of the yarn. It's going to look at the kilograms of force applied. And you can see over here, we did some testing similar to this in my first job to test the strength of rubber and different components, where you'll just stretch it until it breaks and the force at which it breaks is recorded. And here we're looking to maximize that strength. So if we want to set this up in JMP, this is the software I have available. So this is what I'm going to walk you through. We'll look at the DOE menu here, classical, and it's going to give us the option for mixture design. So we'll click that, and it's going to bring up this screen over here. We can set the number of factors. So we have 3 for these 3 different synthetic materials. And here are mixture design types. So we've talked about optimal. In this example, we don't have those linear constraints. So we're not gonna use that. We're gonna skip over simplex centroid for this one, and we're gonna select the simplex lattice. The default number of levels here is 5. So I had to change that. Not really great at writing with my mouse. Default. There. So have to change this. Changed it to 2 because that's what this example is looking at. And so this was kind of specified in the textbook example. Extreme vertices, we didn't really talk about that one so much. ABCD design, that's looking at factor screening, another option we would look at, could look at, and there's space filling, and we can set the number of runs there. So we set that, and then it's going to bring us here. And I think at this point I wrote in names instead of just Y and X's for my factors and my response name. Here's where we could set some of those linear constraints. Now, jump is only going to let you work with 0 to 1. It's going to have you set ratios relative to the other ingredients. Other software like Design Expert will let you work in the actual units that you're working with, which is really preferable, but this is how jump works. We can see these 6 runs that it generated. This is like what I had drawn, the 0, 0, 1, 0, half, half, 0, 1, 0, different order, but the same information. We'd want to randomize it. We can make one replicate and we would make the table. That'll give us 12 points. This is what it'll generate and give us a place for our elongation value, where we could just run the experiments and plug in the results. This example comes with data, and it comes with 3 extra data points for each one of those settings that uses 1/2. So I manually added those last 3 points. So now we've gone from 12 to 15 points. And I plugged in all the observed elongation values that were provided in the example. Then we're going to go here. Once we have that, we can analyze and we'll fit the model. And then we're going to get some exciting stuff. All right, we choose our Y, our response variable. We want to select it so it goes over here. These automatically come up. If they are not saying mixture here, you can change that by going to this little red arrow in the attributes, and it'll give you that option to change to mixture so that it knows that you're dealing with a mixture. Then you'll click on run, and this is part of what you'll get. Now for these responses, we'll want to double check our assumptions. So if we look at residuals here, we don't really see a pattern. Looks like they're really nice within the bounds here for studentized residuals. We've got p-values here for the different effects, and we can see just this bar chart. We can see the actual by predicted plot with this predicted line. Here are all of our actual values, the little black dots. It's looking very good. Then we get to the most exciting part, I think. We have our parameter estimates right here. So we can plug these in. We didn't get into the equation, so we'll probably do that next time. But this is showing how big of an effect either the main effects or the interactions is going to have on our tensile strength, the elongation. And so we see, what's our biggest positive number here? We can see that that's polypropylene. Okay, so we want to use polypropylene. And what's super cool is that JMP will let you in this prediction profiler actually move these, grab this red line and move it. And as you do that, these other ingredients, those ratios will change accordingly as you increase the level of polypropylene. So as we pull that along up to the highest point we can, we'll get to a different kind of graph. It'll kind of adjust to look more like this one over here. And then we see this parabola here on polyethylene. So we can get to the top of that. And we see that that's maximized almost as high as we can get here with our desirability function with about 30% polyethylene and 70% polypropylene. So we can tell give a very clear answer, like here is the best ratio. We don't need polystyrene. But let's think about, what if cost is a factor? If we're trying to minimize cost, that's another response to put in there. Just see, okay, well, how can we optimize the strength of the fabric while we try to minimize the cost? What's the best balance of those two? So we can do that. Here's another tool available in JUMP that is the mixture profiler. It's very similar to what we just saw, maybe not quite as straightforward, but if you want to see different profiles for the different contours. So our result was 17. If we had, 0.7 here and 0.3. So like around here, there's a curve for 17. And then there's this curve for 16. If we want to look at a different value, as we get to smaller values for this example, it starts to go where they kind of circle around these other two corners for those lower values. So some tips and tricks as we kind of conclude this introduction. If you have a mixture kind of experiment, don't use factorial designs. It's when the factors are dependent upon each other in that type of mixture, in that situation, it's not really the best tool. Doing replicates is going to be critical. We want to make sure that we're always doing replicates if we can afford it. Optimal designs are going to be more flexible and practical and probably more fitted to the actual problems we'll be solving. And we don't want to convert, if we can help it. It's nicer if we don't have to convert to ratios, but we do have to in JUMP. So it depends on your software. If we can work with the actual values, it's going to save us a headache. So if we have access to something like Design Expert, and I'm not sure what other tools might be out there that can offer that type of options, that would be more ideal. And we want to spend a lot of time choosing what components we want to use, what we're going to vary, what the ranges need to be, what's realistic for our system. Talk to subject matter experts. Say, is this going to fit? Sometimes experimentation is cheap. More often than not, it's pretty expensive. And so we want to make sure that we're looking at experiments that are actually within the design space that makes sense for our mixture. We also want to be able to think about how do we measure the output of interest? It might be kind of easy. It might be like cost. That's pretty straightforward. This tensile strength, elongation strength that we looked at for the yarn example, that seems pretty easy to measure. But there might be mixtures that we're dealing with that are more subjective. So if we're dealing with a yarn example, let's think about this. I like yarn, I like to knit. And so I brought with me some different yarns. This is acrylic. I don't know, this is one in person would be so much better and you could feel this. But I'm going to put it up to the camera. This is a type of acrylic yarn. I have another type of acrylic yarn. It's not as soft in my opinion. It's a little bit thicker, but the same 100% acrylic on the label. I also have this lovely merino wool. It feels a little bit scratchier. And there's different kinds of wool from different animal fibers. The size, as far as like the diameter, is about the same as the others, but it feels a little different. Then we have a blend. This is 20% wool and 80% acrylic. And I don't know if you can kind of see, it's a little fuzzier. It's thicker and it's a little bit fuzzier. Like the little fibers come out from the yarn more than either of the others. So I just brought this as an example that if we were in a face-to-face classroom, we would pass it around and see the effect of blending, like finding the mixture. If I'm creating something that I want to knit, I might have different response variables that I want to consider. I might want to think about what's going to be the most warm kind of fiber to use in a garment. I might want something that's very soft, so it's comforting for a baby or something. I might want something that's going to endure several washes very well if it's for a baby, like a blanket that might get drug all over the place. So maybe that's something that I'm interested in. If I'm interested in something like softness, how am I going to measure that? What is an across the board good way of measuring that? And in Six Sigma, we've talked about the need for a good measurement system that can be consistent and repeatable. And so just as we plan our experiment, we always want to be thinking about those kinds of factors. How are we going to measure the response? What should the response be? What fits our situation? What are the factors we need to look at? And how are they going to work together? So just spending a lot of time up front is going to save us a lot of time and expense later on, making sure we have the right kind of design. We can always start with something like start with a simple design, and then we can run those augmentation runs to augment it and get more information. We can do that. Also just master building optimal computer generated designs, just getting some experience with that. And so maybe we'll be able to try that out. And I wanted to leave us with an example to get you thinking before our next class. And this is looking at pancakes. I have a friend that teaches culinary arts in Nebraska, and she put on Facebook, she says, as part of our lab, I had the students start with either, I can't remember if she said flour and water or flour and milk, but flour in a liquid, and then make some kind of pancake, and then see what happens when you add an egg. See what happens when you add oil. See what happens when you add baking powder, and evaluate those results. So I was super excited because she's bringing science into her kitchen, and all these kids are getting exposed to kitchen chemistry and experimenting. And I just love that. But I also thought, ooh, this is the place for an experimental design. And this is a place, it's a mixture. The pancake batter is a mixture. So I went ahead and looked up several different recipes for pancakes. You can see them here. We have an option with no egg. I have a recipe for Russian blinis, pancakes from scratch, crazy pancakes, and quick and easy vegan pancakes. We might have constraints, like someone in my family might be allergic to eggs or gluten. So maybe you can't even use wheat flour. So thinking about those things, maybe what constraints are there that you need to work around as you create the mixture experiment to find the perfect pancake for you. And as I was doing some work this semester, came across this Russian blinis recipe, and those are like crepes. They're flat. You roll up either sweet or savory deliciousness in them, and that is going to be a very different kind of pancake mixture than if your ideal pancake is soft and fluffy with lots of air inside, really thick to soak up lots of syrup. If that's what you're going for, then that's going to be a different objective than the Russian blinis. And so just figuring out what is a good pancake to you, what are you trying to aim for, and measure. How are you going to measure that? Can you get calipers and measure the height? How can you consistently put the same amount of batter on the griddle? Like, how would you run this experiment? So I want you to be thinking about this and come prepared to discuss it next time. And if you bring pancakes to class, even better. Thanks for your kind attention today, and I'll see you next time.